Okay. So we are talking about heating curves and cooling curves. This is basically a representation of the process of what happens when you add heat or remove heat from a substance. And then we're going to do the associated calculations involved in this as well. Okay, so that's today. Wednesday will be phase diagrams. And then we might even get into just kind of general review at that point. Friday is all review, and then next Monday is exam 2. Okay, so keep that in mind as you're kind of scheduling things out. And also recognize there's kind of a lot of stuff when you do exam 2. So there's the homework assignment will be due Thursday night, and then both of the practice exams will be due Sunday night. So, starting on the practice exam for chapter 7 today, this week, not a bad idea. And then I'll make sure that the chapter 12 practice exam is posted by, Wednesday after class once we finish that material. Okay, so let me just give you guys kind of a brief. What I did in my last class was I gave an overview of this, and then I have you guys work through a couple conceptual questions and a calculation, and then we go over it. A couple more conceptual questions, calculation, we go over it. Okay? So when we look at these heating curves, obviously first thing to kind of pay attention to is the x-axis is heat being added. This is specifically kilojoules per mole. Rarely are you going to have exactly a mole of something, so you can't just look up values on these tables. They're more to represent visually what's going on. And then you'll do a calculation in order to have a specific number. And then the y-axis is temperature. Okay? So good reminder that heat and temperature are not the same thing. Heat is a type of energy, and temperature is a measure of average kinetic energy. So heat can be converted into kinetic energy. It can also be converted into potential energy. So when we have a substance, we're going to start in this example, we're going to start by talking about a chunk of ice, a relatively small chunk of ice. I think it's 32 grams, which is 32 milliliters approximately. And a cup of water is 240 milliliters. So we're talking about a pretty small quantity here. And we're going to start that at negative 18 degrees Celsius. And we're going to talk about the process of heating that ice cube up, allowing it to melt, and then bringing it up to room temperature at 25 degrees C. So we're specifically going to be looking at this little segment of the heating curve. Okay? So when we heat a substance up, when we add heat to it, and we see a temperature change, that's going to be the points on the curve that have a slope associated with them. Okay, so you're going up in temperature as you add the heat. So that's why we see, a sloped line. Positive slope when we're talking about heating. Cooling is going to be a negative slope. There's an example of that at the very end of today's notes, and I'll give you a sample question for those as well. Okay, when we hit the melting temperature of the substance, now for water, I'm going to assume you guys know that water melting point is 0 degrees Celsius, boiling point is 100 degrees. Anything else I would give you those values for, but I'm going to assume you know that for water. So when we hit that melting point temperature, then we start to see this horizontal flat line, okay? Which means that we're adding heat, we're going along that x-axis, but we're not seeing any temperature change in the substance. Again, heat and temperature, not the same thing. So what is happening here is the phase change. So we've got solid at this, that's not what I wanted to do. We've got solid at this point. We're adding heat, adding, and we are eventually converting it all to liquid. So at this point, what we're really doing is changing the kinetic energy or the motion of the molecules at this point, we're changing its potential energy. So we've got a solid, we are breaking the intermolecular forces. And the way we do that is by heat being added in to break those forces apart. So that's really like a change in the potential energy of that substance. The molecules don't move any faster, they just go to a higher potential energy state in the liquid. So along that horizontal line, we've got like a mix of the solid and liquid, but the temperature doesn't change. So like a real life example of this, you've got your, whatever the coolest new water bottle is. I will never understand how water bottles are cool, but whatever. I've been told recently that Stanleys are not cool anymore, Mom. It's whatever that one, Awala or something. Yeah, that's the cool one. So you've got an insulated water bottle, and you put ice in it, and you put water in it, and the temperature equilibrates, and then it stays ice water, all day long, right? So that ice water, because it's a mix of the two states, is at 0 degrees C. You stick a thermometer in there, it's at 0 degrees C. So there is no temperature change there until all of the solid is converted to liquid. So you leave it in there long enough and heat ends up penetrating that liquid-solid mix. All of the ice ends up melting. Then if you leave it even longer and heat penetrates it, then you start to see an increase in the temperature. Okay, so that would be kind of the third point in this curve, is you add energy in, or you allow energy to come into the system, and then you start to see a temperature change. Okay, so an important point is that the temperature change and the phase change are like distinct, separate processes. So a cool, not really an application, but a time you would notice this is if you take organic chemistry next year and you do the lab, you'll probably do some melting point identification of a particular substance. So you like make a chemical and then you want to see, am I sure I made that correct chemical? One of the ways you can do that is by measuring its melting point and comparing it to confirmed data. So maybe it's like, oh, the melting point is like 150 degrees C. Okay, so the way you do that is you take this little tiny sample in this really thin capillary tube and you stick it into a very, I was going to say simple again, a very simple measuring device. It's pretty much a microscope that you look through it and the sample is heated up. So it has a heating element in there that goes at a very consistent pace, and it also records the temperature. So you look through the thing and you're watching the solid and you see the temperature going up and up and up as heat is added in, and then at some point you see it physically change from a solid to a liquid, and it happens over, like a range of time. But what's interesting is that the temperature stays constant. Okay, so you're watching it, it starts to melt, you look over at the temperature, you write it down, 152 Celsius or whatever, you continue to watch it, all of it melts. During that whole time, it's still 152, and then it continues to heat up, and then you see the temperature change, okay? So it is a distinct, separate process of heating up the sample, having the phase change occur, and then heating up the sample more, all right? And related to that is how we do those calculations. So we've done both of these types of calculations already. The heating it up portions are the Q equals MC delta T that we did in chapter 7. So an important point is that the specific heat of ice, so water in the solid phase, is not the same as the specific heat of water in the liquid phase. So we didn't really talk about that a ton in chapter 7, but it's important to know that the specific heat changes with the substance, but also with the state of that substance. And this is simply because in the liquid phase, you'll notice that the specific heat is a lot higher So those molecules have a lot freer range of motion. They can move around each other a lot more easily. And that means that that heat can be distributed really easily. It can kind of mix through the sample. There's like ways in which it can kind of trap the heat as well. In ice, there isn't that free range of motion. Those molecules are kind of locked into place. And so they're not as good at holding that heat as maybe the liquid is. Once you get into the gas, though, they're really separated from each other. And so it's actually pretty hard, even though they're able to move around, it's pretty hard for them to hang on to that heat because they're so separate from each other that they can't really transfer it a whole lot. Okay? All right, so those two portions, the sloped lines, we use the Q equals MC delta T to calculate how much heat needs to be added to change the temperature. And then the horizontal portion, in this particular example, is where we use the delta H of fusion. So we did this on Friday. If you remember, it was here. So we took xenon, we had the delta H of fusion and the delta H of vaporization. This is in kilojoules per mole. So now we need to be converting, if it is in grams, we need to be converting that into moles. And then we use that to calculate the phase change. All right, so two different types of calculations that we've done before. We're just kind of now combining them. If we were doing the liquid to gas, that would be delta H of vaporization. Okay, so let's have you guys work, with your neighbors, independently, whatever, work through the next page of questions. So it's a couple concept questions and then a calculation. And what we're gonna do is treat all three of these segments separately. So like temperature change, phase change, temperature change, and then put them all together. And then at the very end of class, I'll have you guys do one for a cooling curve that is kind of combine maybe more the way it would be asked on an exam. Okay, so take, I don't know, somewhere in the range of like 5 minutes-ish to work through these three questions. Just this page, don't go past that. I mean, I guess you can, but we're gonna talk about this one before we move on. And in a couple minutes, I'll put up, maybe a couple hints for the calculation. Honestly, I'm not sure you need a whole lot of hints. They're kind of already there. I will start working the calculation. All right, let's go ahead and talk through this. So does the state change when heat is added to water solid at -18? No, you cannot have a phase change happen until you get to either the melting point or the boiling point. So not at the melting point yet. So anytime you're given a substance, you need to first, you can't calculate a phase change associated with it unless it either says it's at its melting point, it's at its boiling point, or it tells you what the temperature is and you can, say, okay, I know it's not at 0 yet, so a phase change can't be happening. Does the temperature change when heat is added? How can you tell? Yeah, because I see it go up, right? The y-axis is the temperature change. So as I add heat, I'm also increasing in temperature. All right, so now we want to calculate the energy associated with taking it from that -18 degrees C and bringing it up to its melting point at 0. So it's still going to be a solid when we bring it up to 0 degrees C, but it's at 0 degrees C, okay? So Q equals MC delta T. Remember, the C is specifically the solid. So 32.0 grams, 2.06. Now I converted this for you guys. No, this is not the one I converted. Never mind. It was listed as that on the chart. 2.06 joules per grams degrees Celsius. Remember, a constant is always telling you what units everything else needs to be in. So if it said joules per kilogram degrees C or kilograms Kelvin, right, then you would need to convert that mass. That's true of any constant, right? When we did gases, R was liter atmospheres per mole Kelvin. That was telling you the pressure needs to be in atmospheres, the volume needs to be in liters. So just pay attention to those. That's, the only way you could really get an equation like this wrong is if you don't have things in their correct units. Okay? Temperature change, final, 0, minus initial, -18. So we know this value should be positive because heat is being added. This is just another good verification. When we do the calculation, we end up getting a positive value. Not 26, 2.06. There we go. So this comes out to be, let's see. I'm not going to do anything with sig figs yet. I'm just going to stop at the ones place. It was dumb because I just put 0, so there's, no good sig figs here. So we'll just go with 1,187 joules for this particular process. So it's just that first segment of the curve, that sloped line. Good? Any clarifications on that one? Okay. All right, second part. Now, this one, I want you to go all the way to this point. Okay, so a little bit more than the page. Again, couple conceptual questions, and then a calculation. Was 5 minutes about right? Was that too long? Okay. I tend to cut you guys off too quickly when I don't leave enough time for calculations often. Okay, so concept stuff. At 0 degrees C, does the physical state change as you continue to add heat? How can you tell? Well, number one, you're at the melting point. And number two, on the curve, it's flat, right? There's no change in temperature. So the only other option is that that energy is going into the phase change. Okay, so, oops. Yes, the physical state changes. We're going from solid to liquid. There's no temperature change. And also, we are at the melting point. In the spot marked 2, which is basically on top of that horizontal line, ice and water will both exist. What is the temperature? Like I said before, if you've got both phases, it's at that melting point. Also, you can just look at the curve and see what is the temperature there. And then at the end of the horizontal line, now you've converted all of that solid to liquid. You're still at the melting point. The temperature hasn't changed, but now you have all liquid. So any subsequent heat that's added is going to go into raising the temperature of that liquid. And then last question, the horizontal line at 0 degrees represents the phase change. The temperature did not increase even though heat was being added. Again, heat and temperature are not the same thing. Heat is energy. Temperature is just a measure of the average kinetic energy. But every substance is going to absorb that energy differently. Okay, so if the temperature didn't change, where did this absorbed energy go to? Maybe a surface level explanation is it went to the phase change. But more specifically, with the stuff that we talked about already last week, it goes into breaking those intermolecular forces. And then finally, for this one, key point, the delta H of fusion that's given is a positive value. That is for solid to liquid. If you were doing liquid to solid, you would need to write that as negative. Okay, because you'd flip the reaction. All right, so this one, calculate the heat required to accomplish the step. That's the horizontal line, the phase change. So we had 32 grams, but this is joules per mole. So I'm going to have to go ahead and convert that into grams. And then I can use that heat of fusion. So molar mass for water, dividing by that, so I get the 18.016, so that I get the moles, which is about 1.78 moles, and then I multiply that by that heat of fusion. Okay, so this comes out to be 10,693 joules. So interesting point, phase changes take a lot more energy, okay? 10,000 joules versus heating it up was only like 1,200 joules, okay? So lots more energy involved in changing phase than in just heating the substance up. Okay, last point, I want you to continue this on, so just a reminder, we're going from -18 up to 25 degrees C, and we've had these 3 steps in the process. So just to kind of summarize that, we did Q equals MC delta T here. We use the delta H of fusion there, and we're going to use Q equals MC delta T here. Often people will be like, well, if you have a temperature change from -18 to 25, why can't I just combine those? Q equals MC delta T's, because the C is different, right? The C is different for a solid than it is for a liquid. So you have to separate them out as two separate calculations. So we did it for this part, that part. Now we're going to do the last piece and then add them all together. And that will be the overall energy required to convert a 32-gram sample of ice from 18 degrees C up to 25 degrees C as a liquid. Okay, so let's run through that last one. And then I'll give you guys a final problem to do that's a cooling curve that's maybe a little bit more, you have to infer all the different steps, not quite so broken down for you. I wish room temperature was 25. I think that's like 78 degrees. It's not really very room temperature. 25 C2F. 77. That's pretty warm. And since we've worked through these kind of in detail, I'll just put up my work and then you guys can double check yours against it. Okay, any clarifications on this one? Yeah.
Where did we get the delta H infusion number from?
So the actual starting number comes from here. So this is for a mole. And then we did the calculation one step earlier here. There. So we took the grams, converted it to moles, and then multiplied. I think that one of the confusion points is this is in joules. I converted it for you. Now this is a good point because it's very likely that you might see it given in kilojoules. So in the heating curve itself, it's given in kilojoules. So I don't know why I converted it for you in the question, but let's pretend that that was in kilojoules. You would need to tack on another conversion in there so that you could add together all three parts, because you can't add them together if they're different units, okay? So if on an exam you come across a question like this, look at the answers and see what units the answers are in. That way you can decide, do I convert the kilojoules to joules or do I convert the joules to kilojoules? Either way, though, they all need to be in the same units. So in this one, I converted them to joules simply because, or I didn't even have to convert them because I gave you guys it in joules.
And why is the 1,187 negative?
Because we're adding heat here to break intermolecular forces, so it should be negative. When we form intermolecular forces, then it should be negative. Did I say negative? I meant positive for the first one. Yep. Yeah, so these ones will always give you the right sign as long as you do final minus initial. But it's a good idea to kind of clarify, am I going up in heat, adding heat, or am I removing that heat? So they should either all be positive or they should all be negative. Okay, let's do one last one. So I'm going to write down a question that would be similar to what you would see on an exam. But in this instance, it's going to be for a cooling curve. So a cooling curve looks almost identical, but reversed, so that we're now going down in temperature and heat is being removed as we go across the x-axis, okay? So we're going from gas to liquid, liquid to solid in these instances. Okay, so the question is, calculate the energy that must be removed from 5.85 moles of water in the gas phase at 100 degrees Celsius to convert it to liquid at, I don't know, let's say 70 degrees Celsius. Okay, so maybe even take the diagram and draw points roughly on what 2 points you're on. And then it kind of tells you if it's a slope line, you know the type of calculation you need to do. You also know it's different than the horizontal line. So if you just put the points on the curve itself, then you can see how many different calculations you're going to need to do before you add them together. So we've got about 5 minutes left in class, so go ahead and work the problem. A couple minutes from now, I'll go ahead and put the answer in, show you the work so you can check your work once you're done. The values that you might need, just go back to that original plot, the heating curve, because this is still water, so the values are still the same. They're going to need to plug into these, like the heat capacity and stuff like that. I'm going to go ahead and leave this in kilojoules. I didn't specify, but just so you can kind of see a different unit. So remember, a good check, they should either both be positive or all be positive or all be negative. Well, that was multiply, not add. And in this instance, they should both be negative because you're removing heat. So assuming I actually typed that all in my calculator right, it should be negative 251 kilojoules. In this instance, you had to convert from moles to grams to do the Q equals MC delta T. Okay, so I put each little, if you want to take a picture, it's fine. I put each little segment, the purple with the purple equation, blue with the blue equation, and then added them together. So draw the curve to remind yourself, is it a one-step process? Is it two? Is it three? All right, have a good day. Yep, see ya.
same stuff as you, like up to the beginning, but then right whenever you gave this as your total, just how did you get that?
So let's see. Did you? Oh, swipe.
I'm sorry.
Okay. So it looks like you didn't do the first part where you converted from gas to liquid. So the purple one is this part where you're at 100 degrees Celsius, but since you started as a gas, you have to first convert it to liquid and then do the temperature change. So I did the moles times the delta H of vaporization, and then I added it to that one that you already calculated.
Okay, because I figured you added something.
Yeah, it's usually going to be, all of these ones, it's usually going to be either a 2 or 3 step process. So it's like, if there's a phase change and a temperature change, you have to treat those separately and add them together.
Good to know. Good to know.
And that's why I said, like, drawing the curve can be helpful, because then you can, like, isolate.
I feel like I would just mess myself up if I do it. That's why I don't do it.
Oh,
Just
okay.
'cause I don't.
Well, maybe just write it down then. Like, the question says energy that must be removed in the gas phase to convert it to a liquid, right? So I'm going to have to go gas to liquid, and then I'm also going to have to go 100 to 70, right? So it's like 2 different processes.
Yeah, like this would work better for me because if I were to do this, I would.
You'd
just,
probably
like,
be like,
I'd be like,
"Ugh."
that means nothing to me.
Yeah,
Like, I would look
yeah.
at it and be like, okay, I'm
Okay,
okay with that.
yeah, do it like this then. So just so you're knowing that
Yeah.
phase change, then temperature change, or temperature change, then phase change, whatever it is.
Okay. So,
Good?
Yeah, and then I added this
And that,
this one.
yeah. And that's where that
Plus.
251 comes from.
Equals that. Okay.
Yeah.
Thank you.
Yep.
All right. Have a good day.
You too. See ya.